So our first quiz on centripetal force and circular motion. We have to have my favorite student, good old Anne. There is an equation which many of you are forgetting about. So number one says a plane turns a complete horizontal circle in 2 minutes. First thing that I did is I said, nice try, 120 seconds. I'm not going to do physics in minutes. The plane speed is 170 meters per second. So they've given me the circular speed is 170 meters per second. And they've given me the period, the time to go around once, symbolized by capital T, is 120, and it wants the radius of the circle. One way to do this, I guess, would be to say circular acceleration, don't write this down, equals circular acceleration would be to go v squared over r equals 4 pi squared r over t squared. And you could now solve for r. Ugh. Speed is distance over time if you're not accelerating. It's meters per second. And when you're going, sorry, I got to be careful. When your speed's not changing. We are accelerating here, but our speed isn't changing. We're accelerating by changing our direction. So, circular speed is once around the circle. This is the circumference. This equation is on your formula sheet on the same page as all the trig stuff and the quadratic formula and all, where you have some math stuff. It's on there, divided by the period. So the equation for speed is not on there, but if you know that speed is distance over time, you don't have to memorize circumference. It is 2 pi r. It's the circumference over the period. And this means I can get r by itself. It's going to be my speed times the period divided by 2 pi. That's how I would do this question. A little easier than trying to let acceleration be acceleration. But, you awake? You sure? Because it's not really going to... You're good? Okay. So, Nikki, you could survive without that speed equation for this, but it's going to be handy in other situations anyhow. So it's going to be, what was the speed? 170 times 120 divided by 2 pi. And you get 3,246, 3,247. And I thought, yeah, that seems about right for an airplane taking 2 minutes to do a big circle. It's probably about a 3-kilometer radius circle, 6 kilometers in diameter. Gut instinct, that seems okay to me just as a number. You know, I like to look at the answer and ask, does it make sense? So I'm going to go with 3,250 meters. 1 mark for that, half mark for that, half mark for that. If you use the letting acceleration equal acceleration method, you would also have got the same thing. I think you would have ended up having to square root your r at one point because you would get the r squared by itself. What's the centripetal acceleration of the plane? Either of those is doable. No matter what, I am going to have to use r, my answer from part A. You know what? This first one is less typing. It's going to be 170 squared divided by, I'm going to write 3,250, but you know I'm going to use my answer button. You get 8.9? So this pilot's pulling just shy of 1 G. Same as before, 1 mark for the equation, half mark, half mark. Oh, well, I guess here, 1 mark, because you didn't have to, the A is already by itself. What centripetal force is needed to keep a 12? Okay, so they want a force. Force equals mass times acceleration, but if it's centripetal force, it's going to be mass times centripetal acceleration. Which equation am I going to use for centripetal acceleration? Depends what they gave me. You know what? They gave me a frequency, which really means they gave me the period. The period is going to be 1 over the frequency in hertz, which is going to be 0.2 seconds. 5 hertz gives you a frequency, so 5 hertz as a frequency means it'll go around once every 0.2 seconds. That's why it goes around 5 times per second, 5 hertz. So I think I'm going to end up using m4 pi squared r over t squared. It's going to be m12 4 pi squared, 6 meters divided by 0.2 squared. If I recall this one, you get a massive answer, which at first scared me until I thought about what was actually happening here. Let me crunch the numbers first. Yeah, 71,100 newtons. Is that right? Now that seemed really high, but then I went, wait a minute, 12 kilograms, that's more than 25 pounds. So think a 25-pound weight on the end of a 6-meter rope, and it's spinning around 5 times per second. That's going to take a lot of force to do that. So at first I was freaking out, and then I said, wait a minute, it should be a lot of force. This thing's moving around very fast. This is a heavy weight moving around really fast. A belt passes over a wheel of radius 25 centimeters, 0.25 meters. Nice try. If a point on the belt has a speed of 5 meters per second, what's the centripetal acceleration? All it wants is a centripetal acceleration. I think I'm going to use v squared over r, because it looks like I can go 5 squared divided by 0.25. I think I can do this in my head. It's going to be, is it 100? I'll put a dot there just so I went to 3 sig figs, not that I would take a mark off for that or anything. Ferris wheel. This is probably going to be a job for a free body diagram. Ferris wheel has a radius of 9 meters. It takes the wheel 45 seconds to go around once. This is a pretty tame Ferris wheel. 45 seconds is a chunk of time. Person who weighs 65 kilograms is sitting on the Ferris wheel bench. What's the force that it exerts? Okay, at the top of the Ferris wheel, which looks like that, what are the forces acting on this person? The obvious one is gravity, normal force. So I think I'm going to have as an equation at the top, gravity minus normal force is what's pushing me in a circle. I've done this dance before where I plus that and minus that over. So we're going to have mg minus fc. That's what equals the normal force. They're going to feel slightly lighter. I doubt there's going to be much of a difference because 45 seconds to go around once. Okay, well, this is a pretty tame Ferris wheel. I don't think you're going to be going, ah! I think you're going to be just enjoying the sights at the top and looking around and saying, oh, nice view, right? M65. Oh, hang on, Mr. Duick, you haven't. It's going to be mg minus mac. You know what? I'm going to use the 4, the pi squared, the r over t squared. And again, Drake, remember, that's acceleration. The most common mistake, kids put that one in for the force. They forget to put the m in front. Force is ma, f is ma, f is ma. Don't forget the m, because that's a sloppy mistake that can be prevented. It's going to be 65 times 9.8 minus 65 times 4 pi squared r over, oh, not all over, Mr. Duick. Just that is over 45 squared. You get 626 newtons. What about at the bottom? Well, at the bottom, let's see, we're going to have gravity down. Normal force is going to be winning. So now my equation is going to be normal force minus mg equals fc. It's going to be normal force equals mg plus fc, or fc plus mg. it's going to be 65 times 9.8 plus 65 times 4 pi squared times 9 all over 45 squared. Rebecca, do you have a good calculator? Have I gone on a rant about a good calculator occasionally? Because I think the equation can be solved just by changing that minus sign right there to a plus sign and not retyping everything, and you get 648 newtons. Not a big difference between the top and the bottom of the ride. That's how you know this is a tame ride. Oh, and not a really big difference between just normal mg, 637. You'd feel this, but you'd have to, you could probably easily, if you were having a conversation with a friend, you wouldn't really notice the acceleration anymore. It's not like something that would be standing out the whole time. Ooh, let's build a circular space station, and we're going to use centripetal force to simulate gravity. So what we said in that case, if there's our circular space station, and here's our astronaut, what were the forces acting on this person? We said really what was occurring was the normal force was what was pushing him towards the center. The normal force is what's pushing me in a circle. We want the normal force to be 75% of Earth's gravitational field. We want the normal force to be 75% of mg. And it's going to be m, they want the period, so I'm going to go 4 pi squared r over t squared. Turns out this will work for lighter and heavier people, grown-ups and children. To get the t by itself, well, t squared is going to be 4 pi squared r all over 0.75 g. How do I get rid of a squared? Square root. So it's going to be 4 pi squared r is 160 divided by bracket 0.75 times 9.8, square root of that, 29.3, is that right? 29.3 seconds. 3 out of 3 if you got the answer. Otherwise, I would give you 1 mark for that. I would give you 1 mark for that, half mark for getting the period by itself, and then a half mark for the answer. Can you give yourself a lovely score at the top out of 16? If you need to lawyer with me, now is the time. It says, example 1, draw a force diagram, a free body diagram for mass little m in orbit. What we're going to start to do typically in our notation convention, Nikki, big M will be the planet or whatever it is that's causing the object to orbit. Little m will be the thing that's in orbit. Could be a satellite, could be a moon, could be an asteroid, whatever. Hey, what are the forces acting on little m? Get the obvious one. Which way would gravity be pointing in this picture? Are you, Duncan, in this picture on the Earth's surface? It's meant to be really obvious. Are you in this picture? Is little m on the Earth's surface? No. Okay. What path is little m tracing out? So here's what we would say. Where must the net force be pointing? Toward the center. Oh, it is. See it? When you're in orbit, the physics looks like this. Gravity is what's pulling you in a circle. But Robbie, because you're in outer space, we cannot say mg. Instead, we have to use Newton's universal law of gravitation. Big G, big M, little m, over r squared. That equals mass times circular acceleration. Oh! Huh. What do you notice? What cancels? Once you're in orbit, Max, it doesn't matter whether you're something as large as the International Space Station or as tiny as a little communications spy satellite, your orbit will be the same. The mass won't cancel when we calculate how much fuel it takes to get up there, but to stay up there, meh. An orbit is circular motion with gravity as the inwards force. But don't use mg. We have to use the universal gravitation equation because the further you are from the planet, the weaker the force of gravity. Example 2. A 10,000 kilogram satellite is orbiting 20,000 kilometers above. Everybody right now underline the word above the Earth's surface. A says, write force equations, and then B says, hey, find the orbital speed. How fast would you need to be traveling to stay in a stable orbit? Okay. What are the forces acting on little m? And I guess I can say, get the obvious one. Yeah. So as a force equation for part A, it would be this. Gravity is what's pulling me in a circle. Gravity is what's pulling me in a circle. What does B want me to find? Don't overcomplicate it. Robbie, what does B want me to find? Did you say speed? I think for the circular equation, I'm going to use the one with the V in it, not the T in it. Okay? So for part B, big G, big M, little m over r squared equals m, and I'm going to use v squared over r. The other question they could have said is find the orbital period. Then I would have used the one with the t in it. That would have told me how long it takes the satellite to go around in its orbit. Although I told you the mass of the satellite, 10,000 kilograms, turns out I didn't need to. Now, we have to be a bit careful here. This distance right here from the very center of the Earth is what we call the orbital radius. I'll call it r orb. What did they give me in this question? What's that 20,000? Is that my orbital radius from the center of the Earth? No. That 20,000 is that distance there. This is 20,000 kilometers. That's from the surface of the Earth to the orbit. So the first question, before I go any further, I'd like to figure out what my orbital radius is. How can I figure out? Yeah. So it's going to be radius of the Earth plus my altitude, because that's really what they gave me, an altitude. Sometimes, you have to read the question carefully, Tori. There will be times when I give you the distance from the center of the Earth. There will be times when I give you the distance from the surface of the Earth. If I give you the distance from the surface of the Earth, James, you're going to have to add the radius of the Earth. So in our particular example, radius of the Earth, I think from your sheet, is at 6.38 times 10 to the 6th, I think. Plus, now 20,000 kilometers, how do I change kilometers to meters? By 1,000. I think that's going to give us 2 times 10 to the 7th. Double check me, but I think 20,000, you add an extra 3 zeros, and you get 2 times 10 to the 7th. So our orbital radius is going to be I think 2.638, but let's find out. 2 times 10 to the 7th plus 6.38 times 10 to the 6th. Yeah, we get 2.638, don't round off, times 10 to the 7th. meters, and that's what's going to go in this equation here. Julie, you okay with that little bit of reasoning there? Okay. Julie, what are we trying to find in part B? Yeah. Now, how would I get the V by itself? What will I do with that R on the right-hand side? So when you do that, you're going to get an R up there. Yes? So you'll end up with big G, big M, R over R squared. That equals V squared. Is there an R on the top, Simone? Is there an R squared on the bottom? Well, one of the R's cancels. So I'll cross out the R and I'll just cross out the squared. Speaking of squared, Julie, I got the V squared by itself. Now what? Yeah. Really, this unit here is why I went on my rant way back in Physics 11 about getting a good calculator. This is going to be, and during this unit, about the most intense pure physical typing into your calculator as you're going to do. And this isn't the equation I have in mind. It's actually going to be in the next lesson, but it starts kind of here. We're going to get this. V, and I typically call it V orb, orbital speed. It's going to be the square root of, so big G is 6.67 times 10 to the negative 11. That's Newton's gravitational constant. Big M, that's the mass of the planet that's causing this orbit. What planet are we orbiting here? Earth. What's the mass of the Earth? It's on your sheet. 5.98 times 10 to the 24th. Divided by 2.638 times 10 to the 7th square. Oh, no, the squared canceled. Square root of that. Typically, if you're in orbit, you'll get orbital speeds in the thousands or in the tens of thousands. There's your little kind of built-in error check. If you get an answer in the hundreds of thousands or higher, you probably forgot to square root. If you get an answer less than that, unless you're really, really far out in outer space, I mean way out there, you probably made a mistake. You do get an answer in the thousands, yeah?
Yeah.
What do you get?
I got 3894.
3894, anybody else?
I got 3888.
I think 3888 is,
I think that's right.
I think is actually correct.
Yeah.
I just remember that number for some reason. 388, so 3890 meters per second. If you are going that fast, you're in a stable orbit and you won't fall. And I wrote here, notice, orbital speed is independent of the mass of the orbiting object. It depends only on orbital radius and orbital mass. In fact, if we wanted to, this equation, I always derive it. It's not on your formula sheet. When I'm in orbit, I always start out with this. Gravity is what's pulling me in a circle, and I can derive just whatever I need to. But for what it's worth, I guess V orb is big square root of big G, big M over R orb. Some of my students, while they're doing this unit, because they use this equation so often, they end up memorizing it. It's not on your sheet. If you do and you jump straight to that in a question, I'll give you full marks. But for what it's worth, you'll see almost all the time, gravity is what's pulling me in a circle. I start there and then I start figuring out what I need to get by itself. Example 3 says, fill in the proof below to show that when an object is in orbit, its inwards acceleration is the same as the gravity field at that distance, which tells us that objects in orbit are in free fall. Say, what? Well, I wrote down here A equals blank. How about V squared over R? That's your inwards circular acceleration. But then it says substitute V equals, what did we say orbit speed was? We said it was big square root, big G, big M over R. which means that V squared equals just big G, big M over R. And if I replace the V squared with that, I get a big G, a big M over, well, it's over R, but there was already an R on the bottom from the acceleration equation, so I'll have an R and an R down there. You could write R times R, but what's a nicer way to write R times R?
Good morning,
Hang on
everybody.
a second.
Excuse this interruption. It's the office speaking. If I could have your attention.
So, R squared. Now, remember, I told you that if you wanted to calculate gravitational field strength, which we symbolize little g, what's little g on the Earth's surface? You all know this from actually Science 10 and Physics 11, Robbie? 9.8, but it gets weaker as you go further up. We said you could calculate that by going, and you get the same thing. Your acceleration up there in orbit is actually calculated by, or it's equal to, gravitational field strength. What this means is objects that are in orbit are in free fall. They're falling. And this bugs people. People want to say, wait a minute, Mr. Dewick, aren't they floating up there? No, they are not. Objects in orbit, every single object that's in orbit is falling to the Earth. Let me say that again. This is crucial to understanding how orbits work. Every single object in orbit is not floating in outer space. There is gravity up there, absolutely. It's in free fall. It's in free fall. It's falling. The real question is, if it's in free fall, why doesn't it come crashing into the Earth? And that's what we're going to talk about. In an ingenious analysis of orbits, good old Isaac Newton imagined standing on top of a large mountain and launching balls from a cannon horizontally. So here's our planet. Here's our big mountain. If we put some gunpowder in, boom. If we put more gunpowder into the planet, into the cannon, which would get the ball moving at a higher speed, it might actually travel partways around the Earth's curve before hitting the ground. And then Newton said, it seems to me that there is just the right speed, orbital speed, such that I could have the ball going so fast sideways that even though it's falling back to the Earth, I've exactly matched the curvature of the Earth with its sideways velocity, so although it's falling, it just never gets any closer because it's moving sideways just fast enough so that the curvature of the Earth is curving away. This is what an orbit is, and this is why astronauts feel weightless in orbit. They feel weightless in orbit the same way I felt weightless when I jumped out of an airplane. Imagine I jumped out of an airplane. The same way I felt that, they feel weightless because there's no normal force on them. They don't feel weightless because there's no gravity on them. And that's why we often talk about astronauts experiencing apparent weightlessness, or you'll hear astronauts talking about microgravity. That's their code for saying, well, we're in gravity, but in orbit, as long as we're in free fall, we can't feel it. So the fact that an object in orbit is in continuous free fall is interesting. First of all, it means that things in orbit are always falling towards the Earth, even if they never get there. It explains why astronauts seem to float around in the space shuttle or on the ISS. Both passengers and the ship are in free fall, falling at the same rate, so the ship cannot exert a normal force, and they experience apparent weightlessness. And it also means that astronauts experience continuously, until they get used to it, the physiological feeling of falling, which is why they're often sick the first couple of days when they're on the International Space Station, and when they come back home to Earth, they're often sick as well. Nerd trivia, I was listening to a podcast, I think it was Adam Savage, Andy Weir, who wrote Adam Savage of Mythbusters fame, Andy Weir, who wrote the book The Martian, and they had one of the directors from NASA on there. And at the end of the Q&A with the audience, somebody said, what's something that we don't know about astronauts returning from the Earth? And the director of NASA said, oh, so here's something we didn't figure out until after the first Apollo mission. When the astronauts come back home, one of the first things they want to do, there's three things. They want to hug their family. The astronauts have been on a long trip, they want to hug their family. So that second thing, they want to chew something crunchy and fresh. They want vegetables. We haven't found a way to get vegetables to the International Space Station with any consistency. We always ship some with any batch of supplies, but that's only once every couple of months. So they really, they get a hunger for fresh fruit and fresh vegetables. They said the third thing they all want is a shower. We haven't figured out a way to get a shower in 0G. So we learned that when astronauts have their first shower, as soon as they close their eyes, they all fall down and hit the ground. So we've had to put railings in our showers, and we've taught them to hold on to their railings when they shut their eyes to put the shampoo in their hair. And the reason is their inner ear has not been in use for about 6 months. And so when they initially are on the Earth, their sense of up and down is purely visual. And when they shut their eyes, they have no idea which way is up and down. So we've taught our astronauts for their first few weeks, when you're showering, grab a railing, soap your shampoo with one hand, don't fall down. Little hashtag nerd trivia. Put your pencils down, look up. In a cartoon, a character kicks the football the wrong way, backwards. But he or she is so strong that the football orbits the Earth and still goes through the uprights, but from the other direction. How fast was the football moving? Okay. Well, I'm going to argue that this path is an orbit, is it not? What's pulling the football around in a circle? So, you ready? Gravity is what's pulling me in a circle. We're talking about orbits and cosmic. Now, Duncan, you might say, I think we're on the Earth's surface. Yeah, we're going to have to use the cosmic universal gravitation equation here anyhow. Big G, big M, little m, over r squared. And that's going to be m. Now, I'm going to write m. Don't write this next bit down. I'm going to write AC, because force is always mass times acceleration. But which circular acceleration do we want to use in part A? Oh, the one with v, because they said speed. Okay. So write this down, mv squared over r. Mass cancels, the little m. When I times the r over to the top, one of the r's will cancel. And in fact, we'll get the equation that we just wrote a little while ago, that orbital speed is equal to the square root of big G, big M over R. Now this is going to be mass of the Earth and orbital radius. We're orbiting right at the Earth's surface. Let's say maybe we're going to go 10 centimeters up. Heck, 10 meters up. You know what? Let's go 40 meters up. That still won't make a big enough difference in the Earth's orbital radius. We can ignore that. How fast will you be going? So it's going to be 6.67 times 10 to the negative 11. Is it 5.98 times 10 to the 24th, I think? Divided by 6.38. Okay. If you wanted to orbit right on the Earth's surface, how fast do you need to go? Just shy of 8,000 meters per second, I seem to recall. Almost 8 kilometers per second. You get 7,900, I guess we round off to 10. 7,910 meters per second. Hey, if you did do that, Drake, what does B want me to find? What do we call what's the fancy term for how long it takes to go around once as a time? Looking forward begins the letter P. Period. Okay, once let's find the period. You know what? We're going to start out the same way. Ready, Drake? Gravity is what's pulling me in a circle. We're still, again, going to go big G, big M, little m over r squared, because we're talking orbits. We have to use universal gravitation, equals m, and it's still going to be AC, but what did you say they're trying to get me to find? I'll use the one with the period in it, which is what? 4 pi squared r over t squared, I think. Did they need to tell me the mass of the football, Drake? They did? Why didn't they need to tell me the mass of the football? The little m cancels. They do need to tell me the mass of the planet, Earth, that's on my sheet. If we do other planets, I'll give you their masses in the question somewhere. What am I trying to get by itself? So this is going to move up to there. Yes? This is going to move down to there. Yes? Will an r cancel this time? In fact, I think you're going to move that to there, and you're going to get an r cubed. I think we're going to get this. T squared equals 4 pi squared r cubed all over big G, big M. Hey, Julie, that's T squared. How to get rid of a squared? That was your cue. You did that one for me a couple of minutes ago, if I recall. Okay. Lots of typing, but doable. How long will it take to go around once at that speed? 4 pi squared 6.38 times 10 to the 6th cubed. All of you must type this in to see if you can do this on your calculators. Every one of you. Yes, Robbie, you too. James is going to try typing this in as well. I would type everything inside, depending on your calculator. Some of your calculators, when you hit square root, is a little sub-window. But for me, I would type everything in, hit equals, and then square root answer button. Four pi squared 6.38 scientific notation button 6 to the 3rd power divided by.
Good morning once again, everyone. Apologies. This should be the last interruption.
On the bottom, 6.67 negative 11 times 5.9. Whoop, I missed a point. 0.98 24th. Square root of that. You get 5,070 seconds? You should. If you don't, later on in class or during flex, you want to come have me help you with your calculator. By the way, if I go divide by 60, it's really every 84 and a half minutes. It's pretty fast. The International Space Station orbits the Earth every about 94-ish minutes, I seem to recall. So Part C. Why is it not possible to orbit the Earth at the Earth's surface in this manner? But it is possible on the moon. Yeah. Air resistance. Because in fact, on the moon, it'd be really easy to set up satellites that were maybe 1 kilometer up. That would probably, I don't think there's any mountains on the moon that are higher than that. Maybe there are, well, really find the highest mountain on the moon, add maybe 500 meters of extra space, and you could have satellites whizzing around up there quite low. No air resistance. What do you know, no problem. But here, even where the International Space Station is, there is some air resistance, so they have to fire a reboost every month or so to boost their orbit back up and to give them enough kinetic energy to stay in orbit. Example 5. If it takes a satellite 300 minutes to orbit the Earth, then how high is it? So now we're going to reverse the question. Let's suppose you are the U.S. National Security Agency and you want your satellite to orbit the Earth every 300 minutes. How high should NASA put it? Okay. Drake, in every orbit question, there are three variables: orbital speed, orbital period, and orbital radius. If I give you any one of them, you can find the other two. How? Gravity is what's pulling me in a circle. Fg equals Fc. Okay. First of all, cross out 300 minutes. How many seconds? 18. Okay, nice try. What does this question want me to find? It doesn't quite. This question wants me to find the altitude, which is going to be, I think, the orbital radius minus the radius of the Earth. So you're right, Duncan, in that although this question wants me to find the altitude, I'm going to spend most of my time finding the orbital radius, but then as my final step, I'm going to say, they want to know how high above the Earth, I'll subtract the radius of the Earth. In other words, if you want a little picture, here's our object in orbit. We're going to calculate this. They want that. So I guess we'll subtract radius of the Earth. Okay. Are we in orbit? Well then, this is how I start out. Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m. Which version of centripetal acceleration am I going to use? The one with the V or the one with the T in it? Oh, they gave me the period? Oh, okay. 4 pi squared r over t squared. Drake, did they need to tell me the mass of the satellite? Oh, nice. That will, by the way, next lesson, when we start calculating how much fuel, then the mass won't cancel because bigger satellites are way more expensive to put in orbit. But here, once they're up there, doesn't matter. What are we trying to find? Okay, so I'm going to multiply this r squared up to there. That's going to give me an r cubed. I'm going to multiply the t squared to there. That's going to give me a big G, a big M, and a t squared. How would I move the 4 pi squared over to the other side? Julie, this is why I picked you. Are you ready? How do I get rid of a cubed? Folks, how do you get rid of a cubed? Holy smokes, you mean cube root is actually useful? They show it to you in math, but holy smokes, we actually going to use the cube root button? And by the way, your job right now is to make sure you know where your cube root button is on your calculator. Yeah, it's going to be cube root. Kind of cool. It's going to be r equals the cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 18,000 squared, divided by 4 pi squared, and then cube root. On the TI graphing calculators, cube root is, if you hit the math button, it's option number 4. There's where cube root shows up. Squared divided by bracket 4 pi squared cube. Oh, hang on, Mr. Dewick. Cube root answer button And you'll get that you want it to have an orbital radius of 1484809.5.9. And I'm going to write the whole thing, 14848.096. So the altitude is going to be this number minus the radius of the Earth. Right? See how lazy I was? I didn't bother rewriting that number twice. You can, but... So this number minus 6.38 times 10 to the 6th. And I get 8.47 times 10 to the 1, 2, 3, 4, 5, 6. 8.47 times 10 to the 6th meters above the Earth. Not enough time, huh? So, but questions you can already do right now. You can start number 1. Number 2, find the speed at which Mercury orbits the Sun. So make sure you use the mass of the Sun, which is on your formula sheet, I think. Did they give me mass of Mercury? I think the mass of Mercury should cancel. Orbital speed. Number 3 is good. 4 is good. 5 is good. 6 is good. We'll assign a bunch more.